So let me remind that last time we talked about principal values of various functions like powers and logs, and we have seen that something is broken because some standard properties that we expect from these functions are not working anymore. But we can also consider multifunctions like log, which is a set of values, and also we have corresponding powers. And now actually some of these issues are fixed. So for example, log of product now is indeed sum of logs. Now we have to be a bit careful about what this means, because remember, these are not numbers. These are sets. And so when we are writing one set plus another set, it means that it's a set where elements are like any element from here plus any element from there. So we add each to each. And correspondingly, we have that power of a product is product of powers. Let me just write proof of the first one. And the other one can be either proved in exactly the same way, or we can use the relation between log and powers. So it doesn't really matter. So let's maybe start from this. And then what we have is, so one set is, so we have log of modulus plus I theta z plus 2 pi I n plus a similar expression, so we have log w plus I theta. And by this theta of z and theta of w, I just mean some value of argument of z and some value of this. So pi I, and now let me call this m instead. And then, of course, when we add any to any, then, and we use standard properties of real log, we get log of modulus of zw plus I theta of z plus, z times w plus 2 pi I n plus m, where n and m are any whole numbers. But then obviously when n and m are any integers, then n plus m is also a set of all integers. So this is the same as exactly the same thing which is exactly log of the product. So it's kind of straightforward. So now if we consider multifunctions instead of principal values, well, we fixed these issues, but there is, of course, price to pay. That now instead of functions, we have multifunctions. And actually, it's all good, but not everything is good. So some things are actually still broken. So let's look at the following examples. So we look at, so actually, if we look at z to the power alpha plus beta, then it's not the same as z to the alpha z to the beta. So this is no longer true. And simplest example is this. So let's take z being 1 and alpha and beta are 1/2. Then, what do we have on this side? Well, we have 1 to the power 1/2 times 1 to 1/2. Well, we know what is square root of 1. It's plus minus 1. Plus minus 1 times plus minus 1. Obviously, product, if we multiply plus minus 1 by plus minus 1, we get plus minus 1. And here we have 1 to the power 1, which is just 1. And clearly, these two sets are different. So basically, what is going wrong here? Well, the problem is happening here. We are multiplying each term by each term. So actually, if you kind of remember that they are coming from the same, like z, then it's natural to think that maybe you should not be multiplying each by each. You should be multiplying. So here we are taking kind of square of these. And then maybe you should be taking square of each element. And then it will work. But then we have to redefine how we operate with sets. So for this to work, we have to combine each element with each element, and then it works. And here we have to do something else. So basically, either we redefine how we operate with sets, or some things are still broken. And this is a bit unfortunate thing, but essentially there is nothing we can do about it. Okay, now let's have a look at another important example. Well, it's not important on its own, but it's a good illustration how all these multifunctions and branches work. So imagine that we want to consider the following function, z squared minus 1 to the power 1/2. So this is a multifunction. It has two branch points. So as we discussed with powers, 0 is a branch point of power function. So here, this is 0 when z is plus minus 1. So we have these two special points. Can we define a single-valued branch of these outside of these 2 points? Well, we'll see what we can do, but let's first try probably most natural, naive approach. Well, we already know what is the principal value of square root. So we must exclude points where our variable is negative, and then we have a well-defined branch of square root. So if we use principal value of square root, then what we need is z squared minus 1 not to be negative real, well, or 0. Okay, so for which values of z, z squared minus 1 is a non-positive real number. So what is the answer?
Yeah? At least one or is less than -1?
Okay, so clearly this, so if we have z is real and between -1 and 1, then its square is less than 1, so this is negative. Do we have anything else? Yes, so if z is purely imaginary, then its square is negative real, and we have negative real. So this is our kind of problematic set. So if we now consider, so it means that z is, well, maybe let's write positive statement. So we subtract -1, 1, and imaginary axis. So if we take z like this, then we can define, then we can use principal value of z to 1/2 to compute some kind of principal value of square root of z squared minus 1. But I think you should agree that it's not really a satisfactory answer. We remove really a lot from our space. And there is another possibility. So let's rewrite this expression as z minus 1 to 1/2 and z plus 1 to 1/2. Remember that this is true, so we can write multifunction like this. Okay, and now can we, if we can define single valued branch of this and single valued branch of this, we multiply, then we get a branch of our original function. And now we can use principal values for both of these. So here we need z minus 1 to be anything but a negative integer. So we exclude this line. And here we need z plus 1 to be not to be a negative real, so we exclude this. So principal values, both of them are defined in C without minus infinity 1, which is, I think, better. But actually, we can do even better. Let's recall what was kind of wrong with this square root, why we needed this branch cut. So when we go around, well, for square root around the origin, or here around this branch point, when we go like this, our argument changes by 2 pi, and so square root changes by factor of -1. So, but what happens if we go like this? Then we go around both branch cuts, and both of these factors will multiply by -1. So the entire function will multiply by 1. So it would not change at all. So it turns out that these two branch cuts, they kind of cancel it out. And here our product is, so this product, square root of z minus 1 by square. So when I use square root, I mean principal value. So continuous. And then it's not very hard to show that since it's continuous, it's also holomorphic. Because our problem was with continuity, that we have jumps. So it just so happens that we have two factors, and each has a jump. And these jumps just kill each other. So we get a nice function. So actually, we can construct a holomorphic branch. So there is a holomorphic branch in C without minus 1, 1. Similarly, I'm not going to define this completely, but you can actually take any two branch cuts going from these two branch points to infinity, and there will be a holomorphic branch in complement of these two cuts, because now you cannot go around any single branch point, so we will not have these issues with square root changing its sign. Okay, so are there any questions about these examples? And if you want to see more details, then you can look in lecture notes. There is very detailed explanation of this example. Okay, so now we move to next stage. So we talked about continuity, derivatives, basic functions. Now it's time to talk about integrals. So we need paths and integrals. So in real analysis, we quite often look at integrals like this. We integrate from a to b some function f of x dx. And in complex analysis, we would like to do something similar. So if you have 2 points, say a and b, then we would like to define something like this. The problem is that here, if you have a and b, well, there is obvious canonical choice. So, well, this is interval from a to b. We integrate along this integral. But there are a lot of different ways to go from one point to another in the plane. And you might say, OK, let's always use straight interval. But what if your function is defined in a domain like that, and you want to integrate from here to here? You cannot use straight line because your function is not even defined here. So we have to discuss paths or curves. So let me just briefly state few definitions. So when I say path or a curve, I mean a continuous function from some interval to c. And sometimes, so a path is just a continuous function from an interval. But sometimes it's also useful to say that, well, this thing is a curve or a path. But this is a geometric object, which is image of our interval. This image is also called path or a curve, which might be confusing, but usually it's clear from context what do we mean, function or its image. Sometimes it's really important to make a distinction, and then I will use this notation. So gamma star means image of this interval. And then we say that gamma is closed if gamma of A is equal to gamma of B. And then it is simple if gamma of T is not equal to gamma of S if T is not the same as S. So it means that curve does not intersect itself. And now to make it more fun, we say that gamma is a simple closed curve. If it's closed, and we have this unless T and S are A and B. So basically, endpoints are the only double points. So it's closed, and gamma of T is not gamma of S for T equal to S, or T and S that are endpoints. So of course, endpoints are the same. There are no other double points. And then we say that gamma is differentiable at some point T naught if the following limit exists as T goes to T naught, gamma of T minus gamma of T naught, T minus T naught. And then, of course, we denote it if it does exist. We denote it as gamma prime. And then we are mostly interested in curves that are continuously differentiable. So usually we assume, so standard assumption is that gamma is continuously differentiable, which means that derivative exists everywhere. And, well, if T naught is one of endpoints, then we look at left or right derivatives. So n derivative is a continuous function of T, or gamma is a piecewise continuously differentiable. So continuously differentiable is denoted by C1. So it means that there are just few points. So we can split our interval AB into finite disjoint union of smaller intervals, such that inside each interval it's continuously differentiable, but there is a finite number of points where it's not. Now, important thing is that if our curve is continuously differentiable and derivative is not zero, then there is a tangent line. So basically, if you have something like this, then it's a differentiable curve. But So if you think about something like that, now we have a corner. And this is kind of piecewise differentiable. So you can have nice parameterization here, and you can have nice parameterization here. But in fact, you could have corners even if your function is continuously differentiable everywhere, but derivative vanishes somewhere. Imagine a curve which is defined something like this. So it's t squared when t from -1 to 0, and it's I t squared when t is from 0 to 1. Then how this curve behaves when t goes from, so when t is -1, we start here, and then we move here, and clearly this is differentiable, but at point 0, derivative is 0. So we kind of imagine that you are driving a car. So, and then you come to complete stop here. And then you start driving in this direction. And this can be done. So you can make sharp corner if you make a full stop. So if derivative, and clearly this function is actually differentiable at 0, it's on both sides derivatives are equal to 0. So if derivative is vanishing, then you could have a corner and your function is still continuously differentiable. And if you allow few points where it's non-differentiable, you could have more complicated pictures. Okay, and then quite often, since we are more interested in kind of geometric notion of a curve, we introduce equivalence. So we say that gamma 1 is equivalent to gamma 2 if, so gamma 1 is, say, from AB to C, and gamma 2 is from some other interval, say CD to F. So if there is some change of variable that we call S from AB to CD, such that gamma 2 of S of t is equal to gamma 1 of t. And in particular, in this case, gamma 2 star is the same as gamma 1 star. So this is just a reparameterization. So we go along the same geometric curve, and we go in the same direction, just with kind of different speed. So this is how you should think about it. And then it's quite easy to see that this is indeed an equivalence. Because if you have two equivalences, you can combine changes of variables to show that it's transitive, and other things are trivial. And finally, another simple observation is that if this S is differentiable, then gamma 2, well, then we have chain rule. And so equivalent, so if we use differentiable change of variables, then a differentiable curve will go to a differentiable curve. So all of this is quite straightforward. And as usual, we say that gamma is an equivalence class. So these are just different parameterizations of the same geometric object. OK. Important thing. Sorry. I have to add one more thing here. So we assume that S of A is C and S of B is D. So we kind of go in the same direction. And this direction is important because we want to make a distinction between this curve, if this is gamma of A and this is gamma of B, and kind of curve where direction is opposite, where so this is the beginning of this curve, this is endpoint. So sometimes we will reverse them, but we have to distinguish between them. So orientation is important. OK, and now when we know what is a curve, we can define integration of complex valued functions. So if we have a function f, which is as always u plus iv, and now this is function of just one real variable, then we can define an integral of f of t dt from a to b as where these are usual Riemann integrals as in prelims analysis. So these are well defined, and we have all these nice results, like if these functions are continuous, then integrals are well defined. If they're continuous everywhere except few points and it's bounded, then it's also integrable, and so on. So we understand this integrability pretty well. And then we will need some properties of this integral. Most of them are kind of trivial. You just inherit them from real integration. But some things are not as simple. So let's look at this innocent-looking lemma, that modulus of integral is bounded by integral of modulus. So in real case, this is essentially a triangle inequality, because by its nature, integration is kind of summation. And modulus of sum is less than sum of moduli. It's just triangle inequality. But now things are not that simple, because we have real and imaginary part, and easiest way to do this is to use the following trick. So let's look at this integral. It's a complex number. It has some modulus and some argument. So we just write it in polar form. And then f of t is a complex number. But now remember that complex numbers, they're kind of two-dimensional reals. So let's remember a little bit of linear algebra. So this is kind of a vector. And this is the same vector rotated by 90 degrees. And they form a basis. Since they form a basis, everything can be written in this basis. So we can write, or rather rewrite, f as u tilde of t e to the I theta plus I v tilde of t e to the I theta. So basically, at each point t, we write it not as real part plus I imaginary part, but we use these two orthogonal vectors to represent the value. Okay? So far, so good? So we have this representation, and well, we know that there are these functions u and t, and also we know that if, well, you can explicitly write these two in terms of u and v using a little bit of linear algebra. But the point is that if u and t were continuous, then these are also continuous. And then we can write integral of f as, well, this is just a constant, so it's e to the I theta integral of u tilde of t dt plus I e to the I theta integral of v tilde of t dt. But we also know that this is r e to the I theta. Well, u tilde and v tilde, they're real, so the integrals are real. And it means that this integral vanishes. So we have two orthogonal vectors. This vector with this coefficient plus this vector with this coefficient. And they are equal to r times first vector. Then coefficient in front of the second vector is 0. And this is r. But then, what is modulus of f? Integral of f, this is r. And this is modulus of integral of u tilde. But now this is just a garden variety, so this is just usual real integral. And for these integrals, we have triangle inequality. So this is bounded by integral of modulus of u tilde. But if you look at these, then modulus of f squared is u tilde squared plus v tilde squared. So in particular, modulus of u tilde is less than modulus of f. And we're done. So it's not terribly complicated. It's just a nice trick. You don't need this trick. You can do it in a similar way like you proved it in prelims. It just will be much harder to write down, and you will be doing a lot of unnecessary computations because you will be replicating all the results. So let's just use it instead. Okay, and now we can define what we really want to define. So imagine that we have a function f from some domain to C, and gamma is a C1 curve such that its image is inside U. Then we define integral of f along this curve gamma. So this is by definition. So this is integral from a to b f of gamma of t, gamma prime of t dt. So this is kind of very natural definition. We write that z is just gamma of t, and then this is dz, and this is z. So it's what you should expect. So it's very, very natural definition, but important thing is that this is a nice complex valued function of single real variable. Well, here we know how to define it. And now we can define integrals of functions along curves. Important thing is that here we really, so this is actually, our integral depends not really on gamma, but it depends on its equivalence class. So we have the following lemma. That if two curves, so if gamma 1 is, so if gamma 1 is equivalent to gamma 2, and they're both, so gamma 1, gamma 2 are both C1 or piecewise C1, then integral along gamma 1 of f is equal to this. So basically, it means that if we reparameterize a curve, then integral does not change. And it's very natural property to have, and it's actually turns out to be quite straightforward. So we just write that, say, gamma 2 is gamma 1 of s of t s of t. So we write this change of variables, and then it becomes just change of variables in integrals. So integral along gamma 2 of f is integral of f of gamma 2 of t gamma 2 prime of t dt with corresponding limits, whatever they are for gamma 2. And then since gamma 2 is this, we have integral of f of gamma 1 of s of t. And then from this, we have that derivative is this. And then we introduce new variable s. This is ds. And so we have integral f of gamma 1 of s, gamma 1 prime of s ds, and here we are. So it's very straightforward computation. So this works if it's C1 or piecewise C1. If it's piecewise C1, then your curve is made of several C1 pieces. Integral over the entire curve is sum of integrals along each piece, and you just use the same argument for each piece of your curve. So that's it. So this is very simple. And now a couple of extra notations. We can define length of a curve. Length of gamma is just integral of gamma prime of modulus of gamma prime dt. And then we also, so this is basically arc length. And then we can integrate function not with respect to z, but with respect to arc length. So integral of f of z along gamma of, so we denote it like this, modulus dz. But this is just a notation. Of course, kind of dz is not a number. It has no modulus, so it's just a notation. But we define this as integral of f of gamma of t modulus gamma prime of t dt. So this is integration with respect to arc length. Now, since all of this is defined in terms of these real integrals, we immediately inherit a lot of nice properties of integrals. So we have linearity, so for example, we have like alpha f plus beta g is in alpha integral f plus beta integral g. So integral is linear with respect to function. Then, so let me just write this and I'll explain notations in a second. So if we have a curve gamma and it has this orientation, then gamma minus is the same curve but with opposite orientation. So for example, if gamma is from A to B to C, so then gamma minus is of T is, for example, something like gamma of B minus well, basically we have B minus T, and now our T varies from 0 to B minus A. So basically it's the same curve, but we go in the opposite direction. Well, again, this is just change of variable, and minus comes from this minus because when you differentiate, you get minus sign here. So, but it's kind of the same as in real case when we say that integral from A to B is minus integral from B to A. So we change direction, we change sign. Okay? And also, we have this very natural property that if we have, so by this I mean that we just glue together two curves. So we have one curve and another curve, and this is just we glue them together as a single curve. Of course, this is equal to sum of integrals, so our integration is also linear, kind of linear with respect to curves, because this is kind of sum of two curves. And we have more general ML inequality, so modulus of integral of gamma f dz is bounded by supremum of f of z, where z is on our curve, times length of gamma. And, well, it's basically the same thing as here. Okay, and the last thing that we will need is the following simple lemma, that if we have a curve, and we have, so gamma is a curve, and we have functions fn that converge to f uniformly on our curve, then integrals of fn converge to integral of f. And this is very similar to what you have seen in prelims. If you have a sequence of functions that converge uniformly on a finite interval, then their integrals converge. Since all our curves are smooth, they are of finite length, so this is equivalent to saying that we look at finite intervals. So this is exactly the same, and proof is the same. Just a couple of small tweaks. So if you look at, so you subtract, then you have this, and this is bounded by supremum of fn minus f times length of gamma. Uniform convergence means that this goes to 0, and this is finite, so we are done. So as you can see, when it comes to just definitions, it all looks basically the same as in real case. But in next lecture, we will see that the same as with derivative, there will be a lot of differences. So definitions and basic properties are the same, but the entire theory of integration is completely different. Okay, thank you.